Welcome again to Advanced Physics for High School Students. This is Lesson 22 and it deals with the inclined plane. There are many situations where we will have objects that will be placed on some sort of slant, and we'll be asked to figure out what the motion of the objects is going to be depending on what the characteristics of the slant are, what kind of surfaces are involved, what kind of forces are acting, and to be able to usually handle friction in these sorts of cases. And so we want to develop the techniques, to continue to develop the techniques, because we've already started talking about them, of how to handle an object that's on an incline. So let me sketch a diagram of an object on an incline, and let's take a look at the forces that are involved. Let's start with a frictionless incline and look at what forces are acting on this box. So we seek to sketch a free body diagram. One of the first things to do is to rotate a coordinate system so that we have one axis that's parallel to the incline and another axis that's perpendicular to the incline, like so. So now we've got to decide what to call these axes, and your textbook calls the part that's parallel to the incline X and the part that's perpendicular to the incline Y. I actually prefer the notation of parallel and perpendicular. So you'll see me referring to the parallel component of force or perpendicular component of the force. The parallel part means the part parallel to the incline, and the perpendicular part is the part that's perpendicular to the incline. Now let's sketch the forces acting on this box. If this is a frictionless surface, there are two forces. One of them is the weight force and the other one is a normal force. Just because the object is tilted doesn't mean that the direction of the weight force has changed. We're assuming that the incline's base is parallel to the surface of the earth and the weight still acts towards the center of the earth, and so that force doesn't change its direction. However, the normal force does have a change in direction. The normal force is the force exerted by the incline to support the box from keeping it to fall directly through the incline. Since it is a surface in exerting a force that is perpendicular to that surface, we call that a normal force. Now we want to resolve the weight force into parts that are parallel or perpendicular to the incline. In other words, ones that are either along the y-axis or along the x-axis. But we've first got to figure out what angle is the angle theta. So let me remind you of this technique that we've used from geometry in finding lines that are perpendicular to each other. So I look at these two sides that form the angle theta, the bottom of the plane and the part that is the other part of that angle theta, the part of the incline. Now, let me see if I can find lines that are perpendicular to those two lines in my force diagram, particularly in the weight vector, and then figure out which angle is theta. So let me notice that if I were to extend this weight vector downward, that the weight vector is perpendicular to the base of the incline. That's going to be one side of my angle theta. And let me notice that the negative y-axis on this coordinate system that I've sketched is perpendicular to the incline itself. So now if the angle theta here between the green and the pink crosshatch is given, then anywhere else there's a green and pink crosshatch that come together is also going to be the angle theta, which is right here in the diagram. So now I want to resolve my weight force into a part that is parallel to the incline and a part that is perpendicular to the incline. So I'm going to take this weight vector and sketch the sides of a rectangle where the weight vector is the diagonal of that rectangle. I'll notice that there are two right triangles in that diagram, and I can use the sides of those right triangles to resolve the weight into a component parallel and perpendicular to the incline. So now I want to get rid of this weight vector and replace the weight vector with its parallel and perpendicular components. But I got to figure out which one's related to the sine and which one's related to the cosine. So off to the side here, I'm going to re-sketch one of those weight triangles, and then let's figure out which part is which. So there's my force triangle. The weight vector is the hypotenuse of that triangle. The angle theta is indicated in the diagram. And now looking at the angle theta and the sides of the triangle that are adjacent and opposite the angle theta, I can see that the perpendicular component of the weight, or the y component, is the adjacent side of that triangle, of that angle, and the parallel component is the opposite side of that angle. Let me pause here to say that spotting various angles and figuring out components to force triangles is going to be a useful technique that you need to develop as you go along in this course. If you're not good at it, then practice is what makes perfect. But being able to sketch these force triangles and to break their forces into components parallel and perpendicular, and to figure out which one's going to be the sine and the cosine related to those parts of the angles is going to be important. What I hope you see now is that the y component, or the perpendicular component, is going to be related to the cosine, and the parallel component is going to be related to the sine. So I'm going to write those things down. And having written them down on this triangle that's to the side, I'm going to add them to my diagram here that's on the inclined plane. Now all my forces are broken into parts that are either in the x direction, parallel, or in the y direction, perpendicular to the incline. And what I can see from this is that the normal force and the Fw cosine theta have to balance each other if there's no acceleration in the vertical direction, the y direction, the perpendicular direction. And it is this unbalanced component of the weight that acts down the incline, Fwx, that causes the acceleration. Since there's no friction in this particular problem, then I don't have to worry about it if I calculate the acceleration. If there is friction present, then it's going to be related to the normal force. Friction is mu times the normal force, and that normal force and the cosine component of the weight are going to be equal to each other if there are no other forces acting in that particular situation. That's kind of how the vectors are broken down. We want to apply it to a particular numerical example. This is the third example that's given in your textbook, and it's one that's worth study. A 93 kilogram block is placed on a plane that is inclined 36 degrees to the horizontal. The coefficient of kinetic friction between the block and the plane is 0.63, and the coefficient of static friction is 0.70. Part A, show that the block will move when released, and B, what is the acceleration of the block. So let's sketch the diagram. There's my block sitting on this 36-degree incline. There are three forces acting on it. Let's suppose that the block is sitting there, and at some instant in time I let the block go. The block is going to tend to want to go down the incline, so any friction that acts is going to be opposite that direction. There's going to be a frictional force that acts up the incline. Now, the problem statement has already kind of tipped its hand, which implies that static friction is going to be insufficient to hold this block in place. But we want to prove, in fact, that it's insufficient. So what we want to do is we want to calculate what that maximum frictional force is. And it turns out that if that frictional force is less than the downward component of the weight along the incline, then friction is not going to be sufficient, static friction, to hold it in place. Let's put the other forces in. There's the weight force, and I also have a normal force, the force that the incline exerts on the block. The next step is to sketch in this parallel perpendicular coordinate system and to break the weight force into components parallel and perpendicular to the incline. So there's my coordinate system, and I've got to figure out which is my 36-degree angle. So I'll play my game again. This leg is perpendicular to the weight force, and this leg is perpendicular to the vertical component of the coordinate system that I've sketched in place. So if the angle between the 1 crosshatch and the 2 crosshatch is 36 degrees, then the angle between the 1 and 2 crosshatch here must also be 36 degrees. Now let's break the weight into components parallel and perpendicular to the incline. There are the components, and I'm going to get rid of the weight force here. And now all my forces are either parallel to the incline or perpendicular to the incline. And I can begin my work. I guess I need to put what the perpendicular component and the parallel component are. The perpendicular component is the adjacent side of that triangle, so FW perpendicular is going to be FW times the cosine of 36 degrees. And the parallel component is FW times the sine of 36 degrees. Now they tell me what the mass of the block is, 93 kilograms. It's easy enough to find what the weight is. The weight is going to be m times g, and that's going to be 930 newtons. So now I can calculate what the parallel and perpendicular components are for this particular incline. The parallel component is going to be 930 newtons times the sine of 36 degrees, 546.6 roughly newtons. And in a similar way we can calculate what the perpendicular component is. It's going to be 930 newtons times the cosine of 36 degrees. And I'll put that into my calculator, and I get roughly 752.4 newtons. Now what? Well, the question is asking me to show that the block will move when it's released. To show that the block will move when it's released is basically to show that the static frictional force has got to be less than 546.6 newtons. If the maximum static frictional force is greater than that, then that means that static friction would be sufficient to hold the block in place. So if I could show that the static frictional force, the maximum static frictional force, is less than 546.6, then I'll have proved my point. Well, what is the frictional force? Well, it's the coefficient of friction times the normal force. And in this case, since we're talking about static friction, then we're going to use the static coefficient of friction in order to make that calculation. But what is the normal force? Well, I can look at my force diagram, and I can see that the normal force acting in one direction is balanced by the perpendicular component of the weight. So I can read off my force diagram and see that the normal force in this particular problem is 752.4 newtons. So I can say that the frictional force is going to be the static coefficient of friction times that number. So let me feed the numbers in, and let's figure out what the maximum static frictional force is. Let me put my numbers in the calculator, and I get that the result is 526.7 newtons. The friction between the block and the plane can only give me something less than 530 newtons of force, but the weight component acting down the plane gives me more than 545 newtons worth of force. Then that means that the block is not going to be able to be held up by static friction. The static friction force just isn't strong enough to hold the block in place. So the block will accelerate. All right, so now we need to calculate what the acceleration is. Well, Newton's second law says that the acceleration is the net force divided by the mass. Well, what net force acts on the block? The parts that are perpendicular to the plane don't come into action because there's no motion of the block perpendicular to the plane. But what I can say is that the weight force parallel to the incline minus the frictional force is going to be the unbalanced force. So let me write Newton's second law in the parallel direction. Let's put in the forces. And you notice that I put the kinetic friction force now because the block is sliding. And if the block is sliding, that means we have to deal with kinetic friction. And that kinetic friction is going to be mu times the normal force, the mu being now the kinetic friction coefficient. So now let's begin to put in some numbers, and we can read those numbers off of our problem and off of our force diagram. And now let's put the numbers into the calculator. When the smoke clears, I get that the acceleration is 0.781 meters per second squared down the incline. So what we've done is we have applied Newton's second law to this inclined plane situation and talked about what the motion of this block is going to be. You can imagine that we could draw in equations of motion to talk about how fast the block is going after it has traveled a certain distance down the incline, but those are things that will come when we mix things together in a later lesson. But for today, that's it.